All right, welcome to AP Chemistry. We're looking at topic 2.5, looking at Lewis diagrams. And our learning objective here is to represent a molecule with a Lewis diagram. And Lewis diagrams can be constructed according to an established set of principles. Those are essential knowledge. So let's go ahead and get started on that. So the established set of principles that we have here are given how to create a Lewis structure. And so these are some steps. We arrange the atoms, start by figuring out the molecule's basic skeleton. This layout shows where each atom is located relative to the others, but does not include electrons. And then we have to remember that hydrogen atoms are always on the outside because they can only form a single bond. And we call these outside atoms terminal atoms. In molecules with atoms of the same type, a symmetrical arrangement is often correct, with a unique atom in the center. The central atom is typically the one with the lowest electronegativity. So that's very important that we know this. It's typically the one with the lowest electronegativity, but it's not always the case. All right, so that's just something to pay attention. It's not a hard, fast rule, and I don't know why I'm having an issue with that, but I am having an issue with that. Let's see if I can get that to work. All right, there we go. It's the lowest electronegativity. So the next thing, and then also I like this thing where they talk about this part where they talk about with multiple atoms of the same type, a symmetrical arrangement is often correct with a unique atom in the center. And that unique atom will often be the lowest electronegativity. So you'll see those two things kind of coincide together very well. So then we're going to count the electrons, the total number of valence electrons for the molecule. And I think we know how to do that. And then distribute the electrons, placing the pair of electrons, a single bond between each pair of the bonded atoms, and then distribute electrons to the terminal atoms first, giving each a complete octet or a duet if it's hydrogen, because we got to remember hydrogen can only have 2 electrons. So after the terminal atoms are satisfied, place leftover electrons on the central atom. And then lastly, complete the octets. If the central atom still doesn't have a full octet, you can convert lone pairs from the terminal atoms into double or triple bonds to satisfy the octet rule. Move a lone pair of electrons from a terminal atom to the bond region to form a double bond if needed. All right, so we're going to just apply those rules. So the first thing that we do is we follow our rules by, see what's going on there, by arranging the atoms. So we have H2O. And so obviously we said that hydrogen cannot be a central atom. So we have oxygen as our central atom. And so let me get a little better pen on that. For some reason, that's not showing up very well. Let's go there. All right, so we have oxygen. And then outside of oxygen, we will have hydrogen. And hydrogen will be considered our terminal atoms at this point. So we've done all of that. Then what we have is a list of the electrons. And so we have, in water, we have hydrogen, which is equal to 2. We have 2 of those in H2O times 1 valence electron each for a total of 2. In oxygen, there's 1 with a total number of valence electrons of 6. And so that's 6, and 2 plus 6 is 8 electrons. Now we have to distribute electrons. Now we're not going to distribute any electrons on the hydrogen because hydrogen is satisfied with only 2. Being in the 1s orbital, can only hold 2 electrons. So now we're going to add our lone pair of electrons to oxygen, 2, 4, and what we notice is 2, 4, 6, 8. So we have a total of 8 electrons, and this is a really good Lewis structure. Then we can do the same thing for HCN. For HCN, we notice that out of hydrogen, carbon, and nitrogen, carbon would be our best central atom because it has the lowest electronegativity, along with being able to pair with other atoms where hydrogen can't do that. So carbon, we would have a hydrogen, and then we could have a nitrogen. And then we do our count. Hydrogen, there's 1 times 1. 1 hydrogen with 1 valence electron is 1. Carbon, there's 1 carbon times 4 valence electrons, which is 4. And then there's nitrogen. There's 1 times 5 valence electrons in nitrogen and 5. And so 1 plus 4 plus 5, that's 10 electrons. So again, we cannot put lone pair of electrons on hydrogen because it's satisfied with 2. We can start adding lone pair of electrons around our terminal atoms. 2, 4, 6, 8, 10. Let's go ahead. Let's go back a little bit. Let's say we have 2, 4, and then let's do this. 6, 2, 4, 6, 8, 10. Now we've drawn 10 electrons, but now we need to check and make sure that everything has an octet or a duet for hydrogen. And so we notice hydrogen has the duet, but carbon has only 4 electrons. So we're short by 4 electrons in our picture. So for every 2 that we're short, we're going to add another covalent bond. Now we can't add a covalent bond between carbon and hydrogen because hydrogen can't take that. So we're going to add a bond here and a bond here. Now when we do that, carbon has 8, but now nitrogen has 2, 4, 6, 8, 10, 12. So we have to remove those 4 electrons that we just added between carbon and nitrogen and take them away. And so what we end up with then is a picture where nitrogen has 2, 4, 6, 8, carbon has 2, 4, 6, 8, and hydrogen has 2. And so everything in the octet rule or duet rule for hydrogen is satisfied. And then we have a total of 2, 4, 6, 8, 10 electrons. So this is a really good Lewis structure. All right, and then we have O3 as an example. And O3, obviously our central atom, I'm not sure what's going on with this thing. This central atom is oxygen, and we have oxygen, and we have oxygen. And so we're going to take our count. Oxygen is 3. There's 3 oxygens times 6 valence electrons for a total of 18 electrons. So once again, we're going to distribute our electrons 2, 4, 6, 8, 10. What's going on with my pen? 2, 4, 6, 8, 10, 12, 14, 16, 18. So then we count and make sure that we have an octet on everything. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. But this oxygen has 2, 4, 6. So we're short 2. So for every 2 that we're short, we have to add a double bond somewhere. Now it's not going to matter where we add this double bond. We can add it to this side or we can add it to the other side. But the most important thing is that when we add that double bond, that we are removing 2 electrons from this atom so that it does not have more than the octet. I'm having some issues with this pin working. There we go. And so we have 2, 4, 6, 8 on that oxygen, 2, 4, 6, 8 on that oxygen, and then 2, 4, 6, 8 on that oxygen for a total of 2, 4, 6, 8, 10, 12, 14, 16, 18. This picture is looking really good. And so that's how we get our Lewis structures drawn for some simple structures. And then we move on into looking at some exceptions to the octet rule. And there are 3 exceptions that we need to be familiar with the octet rule. Those are going to be incomplete octets, or excuse me, expanded octets, incomplete octets, and then also odd electron species. And I may have listed those out of order, but either way, there's 3 of those: incomplete octets, expanded octets, and then odd electron species. So the incomplete octets, there are some elements, particularly those in group 2 and group 13, and form stable molecules with fewer than 8 electrons around the central atom. And so what we see here is this is common for boron, and then boron we notice is in group 3 or group 13. Those elements in that group they will tend to form incomplete octets, or they will have fewer than 8. And as a matter of fact, those in group 13 will have 6 valence electrons in general. So what we'll show is, and this is what this is saying here, we see that this only has 6 electrons. Boron and all the elements in boron, like boron, aluminum, gallium, those are going to form incomplete octets with only 6 electrons. All right, and so that's an example there. And then another one is beryllium. Now, beryllium is going to have an incomplete octet, but with only 4 valence electrons. And it's probably the only group 2 alkali earth metal that we're going to see form a covalent bond. So if we just remember that beryllium is one of those that we have to remember can form an incomplete octet with only 4 valence electrons. So if we look through these, we see that boron in this example has only 6 valence electrons in its supply, and it has the correct number of electrons for BF3. And the same thing with aluminum chloride there. Okay, so we'll move on from that. Same thing with beryllium. It's happy or satisfied or most stable when it has 4 shared electrons instead of a full octet. And these are exceptions to the octet rule. So all others will follow the octet rule, but these in group 13 or group 3A, boron, aluminum, gallium, those are going to form incomplete octets with 6 valence electrons, and beryllium there in group 2 will form incomplete octets with 4 electrons. All right, the next exception would be expanded octets, and it's very important to note that the expanded octets occur in periods 3 or below. So we look at periods 3 or below on the periodic table. They can sometimes have more than 8. It doesn't mean that they will always have 8. Now, when we look at those incomplete octets, those are going to likely always have incomplete octets, whereas these expanded octets may be expanded. They also may not be. And we see some examples for sulfur hexafluoride, phosphorus pentachloride. Here in sulfur, we see 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12, 12 electrons around sulfur. That's much more expanded than 8. And then we see also in phosphorus 2, 4, 6, 8, 10. In xenon, we see 2, 4, 6, 8, 10, 12. And notice how they show the lone pair on there. And we're going to show some examples of that here in a second. Okay, so we've gone over incomplete octets. Now we've gone over expanded octets. And then lastly, we're under odd electron species. So what are odd electron species? Well, there are some molecules that have an odd number of total valence electrons that just simply cannot satisfy the octet rule, largely because the octet rule is the number 8, and that would have sorry, 8 would be an 8. Excuse me, I got interrupted. We got 8 valence electrons, and 8 is an even number, and so we can't have an odd number of electrons and achieve an octet. So here we are with nitric oxide as an example. Nitric oxide has 5 valence electrons from nitrogen and 6 from oxygen for a total of 11. That's an odd number. It is impossible to distribute 11 electrons so that both nitrogen and oxygen achieve an octet. So where do they do with this odd electron species? As you can see here, it is going to be placed on the atom that the unpaired electron usually resides on the less electronegative atom, nitrogen in this case. So one atom would inevitably have an odd number of electrons, and the unpaired electron usually resides on the less electronegative atom. In that case, would be nitrogen. So let's look at ClO2 as an example. In ClO2, the first thing we do when we draw Lewis structures is we say, okay, Cl And again, I'm going to go back and use my purple pen. We see we have Cl O2, and chlorine is less electronegative than oxygen, but also it is fewer in number, so it's probably going to be in the center. And so this is where we show this symmetry on both sides of the chlorine atom. Then we do our count. Chlorine is equal to 1. There's 1 chlorine times 7, which is 7. Then we have oxygen, and there's 2 of those times 6, which is 12, for a total of 19 electrons. All right, and so now what we're going to do is we're going to distribute our electrons so that we can get an octet on everything, except where we know we have an odd number of electrons, so it's not going to happen. Remember that one atom will have an odd number. The unpaired electron usually resides on the less electronegative atom. So our lone electron should be on chlorine because it is the lower electronegative atom. So we're going to fill out these oxygens first. I'm not exactly sure what's going on with this pen, but hopefully we'll get it resolved. All right, so what we see here is we're going to have 2, 2, 4, 6, 8, 10, 12, 14, 16, 18, and then 19. And so we show it with the 1 electron there. Why? Because we don't have enough electrons. It's an odd electron species. And that's as simple as that is. And so everything has an octet except for chlorine, which has that one lone electron. And so we would say that this is a good drawing. All right, and so check. All right, and just to review, we have types of bonds. We have incomplete octets, expanded octets, and then odd electron species. And there's some common central atoms that you see with that. All right, now moving on, we're going to see that I have some examples here. And so we have beryllium chloride. Beryllium, as you remember, is from group 2. And since it's from group 2, we know it's one of those that is going to form an incomplete octet and is going to be satisfied with 4 electrons. So the first thing we're going to do is we're going to write out the structure Be and then Cl and Cl. And again, we see the symmetry, but we also know beryllium has a lower electronegativity. So we show beryllium, there's 1 times 2 valence electrons for 2. And then chlorine, there are 2 times 7 valence electrons for 14. That's a 14. 2 plus 14 is 16 electrons. So we're going to distribute our electrons till we achieve an octet, except for beryllium. So 2, 4, 6, 8, 10, 12, 14, 16. Now, normally we would say, okay, well, we need to add 2 more on beryllium, but since we know beryllium forms an incomplete octet with only 4 electrons, we're going to leave this one alone. And it is an exception. So otherwise, we would have put some double bonds in. However, beryllium is an exception to that rule. Then we look at BCl3, boron trichloride. We see boron with 3 chlorines. Again, we see these around the boron. We put in our count, 1 times 3. 3 valence electrons is 3. Cl is 3 chlorine times 7 valence electrons for 21, for a total of 24 electrons. And so all we have to do is do our electron count till we get to 24. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now we're satisfied with 24, but notice boron does not have an octet. Is that okay? That is okay because boron is an exception to the octet rule and is more stable with only 6 shared electrons And so we can say that is good and we don't need to do any further work. All right, so we can do the same thing for gallium trifluoride. It's going to follow a similar pattern. Since I'm running out of room over here, since I'm running out of room over here, I'll do this over to the side. Not that it matters to you, but so we have GA and we have F3, and this is going to follow something very similar. Because what we notice about gallium is it's directly under aluminum, which is directly under boron. It's in group 13 or group 3A. And so these are going to form an incomplete octet. So our count is very similar to what we just saw. Gallium, there is 1 times 3, which is 3. And then fluorine, which is 3 times 7, which is 21, for a total of 24 electrons. So we put in our count: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I think I counted wrong. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We're not going to give gallium an octet because, like boron, like aluminum in group 3A or group 13, these form incomplete octets. And so that would be a good structure. All right, so let's go into sulfur hexafluoride. So here we have our structure, sulfur, and then we have some fluorines around here. We're going to have 6 of them. And then we have to do our count. So sulfur, whatever reason that's happening, I don't know. But so there we go. We have sulfur, which is 1 times 6, which is 6. And then we have fluorine, which is 6 times 7, which is 42, for a total of 48 electrons. We go ahead and give everything an octet. So there's 8, 8, 8, 8, 8, and 8. And 8 times 6 is 48. So all of the fluorines have an octet, but the sulfur has more than an octet. And that's okay because sulfur is in period 3 or below, and it can form an expanded octet. It's an exception to the octet rule. And so that's just what we have there. Then we look at ClF3. In ClF3, we have chlorine followed by 3 fluorines. So we draw out the structure. We're going to do our count. Cl is 1 times 7, which is 7. Fluorine, which is 3 times 7, which is 21. And 21 plus 7 is 28 electrons. So we can have 28 electrons in our picture. So we're going to show 2, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and then we got 4 more pair of electrons, or we got 2 lone pair of electrons to go. So we're at 24, and this would be 26 and 28. Now, if you look at normally, when we were looking at double bonds, we were short electrons, right? We didn't have enough to distribute in order to get to the octet. Here, we have more electrons than we need. And is that okay that we add those to chlorine? And the answer is yes. Why is that? Because chlorine is in period 3 or below and can form an expanded octet. So we are good with that picture. All right, and then lastly, we have XeF4. So Xe, F, 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 and F. And we put this in. Xe has 1 times 8 valence electrons, which is 8. Fluorine is 4 times 7, which is 28. And so we're ending up with 36 electrons. All right, so 36 electrons. And so we count, we add our octet. And what we notice is we have 8 times 4, which is 32. And so we need to have 4 more electrons. Again, we're not adding a double bond because we have more electrons than we need. And so this means this is probably that Xe can have an expanded octet. And since Xe or xenon is below period 3, we can add the lone pair of electrons, something like that. And now it shows 36 electrons. And that is a really good picture. All right. And so that covers everything with Lewis structures and being able to represent Lewis structures with Lewis diagrams. And so thank you for watching. Please like and subscribe.